Hello everyone, this is your instructor Kurt, and I am going to go through a couple of slides that address the items that you were asked to talk about in discussion post number 1. I'll start off with the terminology first so that we can be clear on what the terminology is, and then we'll go through some of the values. You're given a very small data set and asked to calculate things like mean, median, mode, and those kinds of things. So I'll go through a slide that shows you kind of what those values are. And I'm going to go into a little bit more detail than you were asked to go into. And this is just for your information. It's nothing that you need to really worry about at this point in time, but I'm going to go into a little bit more depth on some of my descriptions of the terms and the process for calculating some of the values. Let's get started. I'm going to talk about descriptive versus inferential first. A lot of you kind of figured out that descriptive is basically looking at an entire data set. So what we're doing when we're doing descriptive statistics is we are calculating values that relate to the whole data set or what might be the whole population. So when we calculate a mean, or when we calculate a median or a mode, or even some of the other values that you were looking at, and we're able to get to the whole population, then we're able to use descriptive statistics and just tell kind of what is in the data set, looking at the whole data set, and without having to do sort of any kind of inferential work. When we get to inferential work, then we're usually in a situation where we can't analyze the whole population just because we don't have access to the entire population. So what we're doing instead is we are coming up with a representative sample of the population, and we're running our statistics on that representative sample. This is key for you who might want to do quantitative methods. One of the key areas where the quality of research can be really impacted is the way that the sample is selected. So when we select a sample, again, it has to be representative of the whole population. Otherwise, whatever we determine in our statistical tests about the sample is not going to be generalizable back to the population. And we really want that. We want to be able to say something about the sample that we can show and defend that it applies to the population as well. The way that we do this is we'll come up with a representative sample, and we'll take a look at our data set, some of the variables that we care about, and some of the meaning behind the variables that we care about, and we may state some hypotheses about that sample. We may say that variable A and variable B are correlated, just as an example. And so that would be something that we want to test. We want to test and see if, in fact, they are correlated. It means that when one goes up, the other one goes up or goes down in a predictable manner. We would go about this by stating two hypotheses. The first hypothesis that we would state would be the null hypothesis. And a null hypothesis is a statement that basically says there's no relationship. There's no relationship in the sample. So if we were checking the correlation coefficient between variable A and variable B, our first hypothesis, our null hypothesis, would be to state there's no relationship between variable A and variable B. The second hypothesis we come up with is an alternative hypothesis. And that states basically what we're looking for. We would state that there is a relationship between variable A and variable B. What we go through then is a process of testing through statistical tests our first hypothesis, our null hypothesis, that there is no relationship. And we try to sort of prove that there is no relationship, or we try to see that there is no relationship. And if in fact we can prove that there is no relationship, then we have to accept the fact that there is no relationship. What's very often going to happen is that we will test our statement that there's no relationship, and we will find that we cannot support that statement, that we do see a relationship. So we have to reject the null hypothesis. And in rejecting the null hypothesis, that allows us to accept the alternative hypothesis that there is, in fact, a statistically significant relationship between variable A and variable B. Once we're able to support that in the sample, we can then try to generalize that back to the population, assuming the sample does a good job of representing the population. There's a bunch more on this to come. Many studies, especially the ones you'll be looking at in this class, use inferential statistics. They use the process I just described. They state a null hypothesis, and then they state an alternative hypothesis, or a series of hypotheses, and then go through the statistical test to try to prove or reject the null. Again, more on this to come. All right, let's talk about mode, median, and mean. Many of you figured out that mode is the value that occurs most frequently in a data set. And the reason why I'm bringing this up is that there are some data sets that will throw you a curve. And what that is some data sets first have multiple modes, meaning that there's a two or more values that are repeated the same amount of times. And so those become multiple modes. You might have a mode of 3, a mode of 5, and a mode of 10, because all three of those numbers show up the same number of times in a data set. Alternatively, you could have some data sets that have no modes. Every single value in the data set is unique and nothing is repeated. And so you would indicate that that value or that data set had no mode. Median is the point in the data set where 50% of the values are higher and 50% of the values are lower. And the reason why we use it is to protect ourselves or protect our analyses from very extreme values. And a good example of that would be housing prices in Seattle. Whenever you hear any news stories referring to housing prices in Seattle, you never hear mean house price in Seattle, you hear median house price in Seattle. Because you may have 95% of the house prices in Seattle that fall within a certain range, but you also have that other 5% that is so far out of the range that to calculate the mean would come up with a value that is artificially high. So we use median instead so that we can protect ourselves from those artificially high or artificially low values. What happens, however, when we have an even number of non-repeating values? For example, in the sample that I'm showing you there, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What is the median of that? Well, if you look at the middle point, the midpoint, you've got basically 5 and 6, right? You'd have to account for 5 as being in the lower half and 6 as being in the upper half. And there's no nice, clean value between 5 and 6 to give us a real median. So what we do in a case like this is we take the two middle values, 5 and 6 in this case, we add them together and divide them by 2, and that becomes the median of the data set. And then the mean, of course, is the straight average. We just add up all the data points and divide by the total number of data points. What is an outlier? You'll hear me refer to outliers often. Outliers are extreme points, extreme values in a data set. And they're problematic in a lot of ways. They're problematic because they could throw off your analyses, or they could actually be erroneous. They could be errors. They could be values that are so far out of the range that it could be somebody keyed it wrong or somebody entered it wrong, or it's just, but anyway, it's going to throw off your analysis. Now, we have to be careful about just eliminating outliers because sometimes outliers are valid measures. And if we do that, we've biased our work. But here are a couple examples. I have a data set that has 9 values in it. My mean in that data set is 24.3. And if you look at each one of those values, none of them strays very far from 24.3. My median is 24. So it shows me that my median and my mean are very close to each other, which tells me I have a fairly tight scatter around my mean. That's just basically saying that all your data points are close to the mean. My standard deviation is also fairly small. Standard deviation is when you're calculating the mean, if you have a standard deviation, that is the value. If you take that and add that to the mean or subtract it from the mean, 68% of your values will fall into that range. So again, it's just an indicator of the level of scatter around the mean. If I take my same exact data set and I change one value to throw in an outlier, instead of 27 I have 57, my mean doesn't go up that much. It goes up a bit, but it's not huge. My median is still 24, which is again why we use medians, but my standard deviation is out of whack. It's way out of whack, and that's thrown off by that 57, that single value. So it becomes an issue of whether or not do we eliminate that 57 value or how do we correct for that. It's mostly a fairly tight distribution with just one exception. And then my outlier, again, I have to think about, is my outlier real data? Is that a real measurement? Is that a real measurement that falls within a range that I would accept? Or is that something that looks like it was put in there in error? Let's talk about variation. And variation is different from variance. I saw some confusion between variation and variance, and I'll talk about variance later. Variation is really another word for it is range. It is how far of a distance is there from your highest value in your data set to your smallest value. And we call that range. And it actually can be measured by taking the highest value in the data set, subtracting out the smallest value in the data set, and that becomes your range. We use something also, again, to get around outliers, extreme values, extreme low values, or extreme high values in the data set, called interquartile range. And what we'll do is we'll take a data set and we'll divide it up into 4 parts. It's the lower quartile, the second quartile, the third quartile, and then the top quartile. And those are basically you get that by taking your data set, sorting it, and then dividing up into 4 equal parts. The interquartile range that we look at is for the 50% that exists between the point where you're at 25% and the point where you're at 75%. And interquartile range, again, we're looking at that. oftentimes to eliminate extreme values and outliers. And I've got an example down there below where you can see the 4 different ranges, 0 to 25, 25 to 50, 50 to 75, and 75 to 100. And you see that the interquartile range are those values that fall between the 25th point and the 75th point, or the 75th percent point, where it's the middle 50%. Anyway, that's interquartile range, and we'll use that a lot of times just to take kind of a quick look at a data set. What is normal distribution? Well, first thing we do is we calculate the mean, and we'll plot that mean, and we'll use generally a histogram or some other graphic to plot that mean. And then we'll plot the data points down and how they scatter around the mean. In a histogram, it's easy because we just put them in bins. Bins of some value. It could be 5 points, 10 points, 20 points, whatever. And you'll see how easily the data points scatter around the mean. If what we generally expect would be a normal curve, which means that you're going to have a normal distribution around that mean. And I'll show you some graphics of what that looks like. And what we're trying to see is, do most of the data points approximate that mean? Are they just a little bit off? Are the majority close to the mean? Or do we have a much wider spread? Is there a wider variation around the mean that could be caused by outliers or some other artifact in the data? Here is an example of 3 different types of distributions. The first one is a normal distribution. Your mean is going to be right there in the center of the histogram. The bins are 10, so you've got 10 to 20, 20 to 30, 30 to 40, and so on. And you just distribute your data points in each of the bins, and then the height of the bin, of course, shows you how many data points you actually have. That would be a very nice, clean, normal distribution underneath a bell curve. And we can see that our data are nicely scattered evenly around our mean. Over to the right of that, we have what's called a skew. And a skew is where your data points, they sort of look kind of like a normal distribution. But what's happening is you've got a lot of values that are higher or lower. This happens to be a positive skew. So you've got a lot of data points that are skewed out to the right. Those are outliers, and those are a lot of outliers. The majority of your data scatters around what looks to be a mean of about 1.1 to 1.5, but then you've got a really long tail there that goes out to the right. Or you could have it the other way with a really long tail. Your data points are on the right side, and your skew or your tail is going over to the left. That is not a normal distribution. That is a skewed distribution. And you can have either positive, as in this case, positive skew, or if your tail was on the other side and your data points were on the other side, you'd have a negative skew. And that can impact the way that we actually look at our data because you can see the outliers there. We also have another characteristic that we look at. It's called kurtosis. And that's at the bottom there. Kurtosis helps us get a better understanding of how our normally distributed data set actually looks. So we could have the mesokurtic. The mesokurtic is a normal distribution. And that's what we see in the upper left-hand corner there is a normal distribution. But if you look at the shape of the other two, those are normal as well. There's no skew. We don't have outliers that are pulling a tail either to the right or to the left. But what we do have is we do have longer tails and shorter tails. The pieces on the right and on the left in a normal distribution, or in any distribution in fact, are called the tails. And what we would expect to see is there to be a sort of regular shaped tail on either side. But in a leptokurtic or platykurtic distribution, you have a normal distribution and you have the same number of data points on both sides and you don't have any real outliers or real extreme outliers. But it's just not a normal distribution. In a leptokurtic distribution, everything is very close to the mean and everything's sort of packed in around the mean and you have very short tails. But in a platykurtic distribution, you don't have everything grouping around the mean. In fact, you have a much broader spread and you have much wider tails. So that's the difference between a normal distribution, a skewed distribution, and a either leptokurtic or platykurtic distribution. Okay, let's talk about the values that you were asked to calculate. So you were given the 2 columns in the upper left, the gender and the weighted total. And so what you were asked to do first and foremost was to calculate the mean. And you can use the average function. And the average function is going to get you to a point where you can calculate a mean of 93.89. You were also asked to calculate the median, which in this case is 96, and the mode, which in this data set is 99. I put the caveats here, which I already talked about, is remember when you're calculating median, what happens if you have non-repeating even number of values, and you have to come up with the median. In this case, remember, we would take 3, add it to 4, and divide it by 2, and that would become our median. A caveat on mode is, what if we have either values that do not repeat, so there is no mode, or we have multiple values, as in this second case, we have 2 2s and 2 4s. We have multiple values that repeat the same number of times, so in this case we have 2 modes. We have a mode of 2 and 4. Our variance, which you were asked to calculate, is variance of the sample, and we'll talk later about why you would look at one that is sample and one that is population, but in this case we're looking at sample, and that came out to be 51.86111. And the standard deviation was 7.201. Your minimum value is 99, your maximum value is, or your minimum value is 77, your maximum value is 99, thus your range was 22. Your range, or your variation, was 22. A little bit more detail on how to calculate those values and why those values are important. So what we're doing is, when we look at the mean, these are the actual values, these are the actual values, and we're comparing that to the mean, we will calculate what's called a differential. And a differential is the difference between the difference between the actual data point and the mean, and that will give us a value. And each one of these is going to give us a value, because not any one of them is going to be the exact mean. There may be a case where you have one that's the exact mean, but typically the mean is the value that the data points are scattered around. So there's going to be some difference between the actual data points and the mean. We'll take those differences, and if you look at them, some of them are higher and some of them are lower than the mean. If we were to subtract the mean from the actual data point in every one of these cases, we would get a series of values that are positive and a series of values that are negative. The problem with that is that when we go to add all those up, because we want to come up with a value that represents the entire sample, they'll cancel each other out. And so we'll wind up with something that's fairly close to 0. So what we do instead is we take the difference, we take the weighted total, in this case 96, we subtract out 93.89, and we take that value and we square it. We come up with a squared value, because a positive times a positive is a positive, and a negative, which would be in this case, a negative times a negative, is also a positive. So we come up with positive values, squared values, these are squared differences, that represent the difference between the actual data point and the mean. When we add all these up, we come up with a sum of the squared means, or sum of the squared differences, I should say, not means, it should be sum of the squared differences. And that comes up with a value of 414.8889. Then we want to come up with the average squared difference. And so we take that in the sample, we take all these, and we're just calculating a mean. So we add these all up, we come up with 414.8889, and we divide it by 9. And that gives us a value of 51.8611125, which is our variance. And it's the same variance that Excel gave us. So that's how we calculate variance, is we come up with the difference between the data point and the mean, we square it, we add it up, and we calculate the average, and that comes up with our variance. The next, but keep in mind, variance is, it's the average variance, it's the average squared variance across these data points. And the problem with that is that it's still squared. And if we want to come up with something that is truly representative of the variation in the data set, we'll take the square root of the variance. The square root of the variance gives us 7.2014 and all those other digits. That becomes our standard deviation, and it's the same standard deviation for the population that we got when we calculated through Excel. So that, again, is way more information than you needed. You were just asked to calculate these values here. But I wanted to try to give you some explanation for where variance comes from and where standard deviation comes from. Because you can fairly easily take a data set, come up with the mean, calculate the squared differences, come up with a sum, come up with the average, take the square root, and manually calculate your standard deviation fairly easily. Okay, that is enough of that. If you have any questions, feel free to reach out to me and email me. Otherwise, I will be looking through your discussion board posts, but I wanted to give you an idea of what it was we were actually doing. Okay,